My pleasure today to introduce our speaker, Tiffany Allen. She is a soil survey office leader in the Waynesville, North Carolina office. And she is a passionate and enthusiastic adopter of digital soil mapping. So I know she'll have a lot of exciting things to share with us today about her experience and progress on this particular project. The Digital Soil Mapping Focus team had the opportunity to work with her and her project staff on our first DSM Field Week in October 2018. And that Field Week focused on an update project in the Great Smoky Mountains National Park. And Tiffany is going to give us an overview of the project and what they've been able to accomplish so far. So Tiffany, I will turn it over to you.
Thank you, Suzanne. Yes, so I want to start off by first and foremost thanking Suzanne for allowing me to present our project to you guys today. And I am an enthusiastic DSM practitioner. I think it has given us an opportunity to really expand our skills and to think outside the box. And at the same time, maintain our scientific integrity. So it has so far been a good experience, and I also want to thank everyone that had any part in the success of our project. Your participation and assistance is much appreciated, and hopefully I can pay that forward someday. All right, so I'm going to start off by talking about our project. There's been several phases of our project, so I'm going to really just start off by talking about what the project was, what we did, get through the portion of where we're modeling and our result, and then I'm going to go into some of the lessons that we learned and knowledge that we gained by doing this project, and the hope is that we can save you some heartache if you ever want to do this in your own office or in your own work that you're doing. All right, so the product development, and I think some of you kind of are familiar with this project, so this will be a little repetition for you. But for those who are just learning about this project, basically we started in November 2016 when we had the chimney top fires in the Great Smoky Mountains National Park. So we were asked to assist the BEAR team, Burned Area Emergency Response Teams, to look at the soils and assist in kind of understanding what the burn severity of those soils were. And what we observed while we were out there was that there were high-risk areas on those greater than 50% slopes that had rock fragments exposed on the surface. Those particular areas were more prone to mass movement than, say, other areas in less sloping soils with less fragments. And the soil survey, the current soil survey, because the Great Smoky Mountain National Park is actually a published soil survey, the information that the Surgo product actually gives right now didn't necessarily accurately depict the differences in landforms. So we're talking about really the difference between residuum and colluvium. And so we also wanted to narrow the variations between that 30 to 50% slope and 50 to 95% slopes, because as we said, those are the difference between maybe moderate limitations or moderate severity to mass movement versus maybe a higher risk to mass movement. Again, the intent was really to more precisely predict the specific soils found in the NRCS geology, which is an acidic geology, black slate essentially, on residual and colluvial landforms, and to improve their use in interpretation and use in management. So here is a picture of the initial, this is basically the existing Surgo that there is now, and so what you can see is that, based on the tools that they had at the time, that this is kind of the product that we have. And so a lot of the colluvium in this particular area isn't delineated. And so if anyone else kind of wondering what NRCS geology looks like, The picture here is one of the burn areas. That's the chimney top. So what happens with that is that it actually got so hot, it sort of blew up. And what you have are the trails pretty much gone. And so where you see all these fragments exposed, those were sort of the high-risk areas that we were kind of looking at. And so phase one really began in March 2018. For Chad Ferguson, he had to talk to me a lot through that initial process of trying to figure out how to use GRASS. We utilized GRASS to develop a landform model. So some might be familiar with Geomore Funds. If I say that again, at least you'll know what that is later on in this presentation. We also utilized condition Latin hypercube sampling, that's utilizing RStudio and Covariance to develop a stratified random sample, and then we would use those sampling points for our field investigation. And then the intent was to develop the model in ArcSIE, which is basically utilizing knowledge-based raster soil mapping using rule-based reasoning. So utilizing your tacit knowledge and using your rules to develop both a raster product and also a vector product that would then go into a traditional Sergo product at the end. And we were focusing on soils within the Arcos or black slate geology that exists within elevations of greater than or equal to 950 meters. So that was phase one. So what we did was we buffered out about a quarter mile off the trails and ran CLHS and got in there. But what we realized is that the way that we had set up this entire project based on the boundary and using that buffered area is that the computer doesn't care how hard it is to get to a particular point. It also doesn't care how close these points are to each other. So you may get on a trail and you could hike 10 miles and get 2 points, and it would take you 3 hours to get to 1 point. So that really isn't necessarily efficient use of your time. So we had to go back to the drawing board after phase one and kind of figure out, a better system for sampling out our points through CLHS and making efficient use of our time while we were out in the field. So this is just sort of a picture of how far off the trail the points existed using that quarter mile buffer and how close they were actually together. So then we went to phase two, okay? So that was sort of an immediate learning curve. We had a week of field work and we realized that we needed to go back to the drawing board. So we went to phase two. We still use GRASS and Geomore Funds with our landform model, and we use condition Latin hypercube, but this time we narrowed the covariates down to slope and landform. Initially, we were using slope, landform, elevation, and aspect, but what we realized being out in the field is that aspect wasn't necessarily playing a part, and the elevation DEM, the project itself was set up at a specific elevation, so the elevations weren't really playing a part at that time, a part in the modeling process. We still were going to use ArcSIE in the end, but we needed to narrow the scope, so we confined the scope of the modeling area directly to what was called the off-30 raster from the Great Smoky Mountain National Park. So this off-30 basically was a ground truth raster that anywhere within that raster grid, you were 30 minutes off the trail. So that allowed us to make really efficient use of our time by not getting too far down into any one area, crawling through rhododendron thickets so that we could capture more points in a day. And so as you can see, the same area that was before, where your points are now closer together, closer to being off trail, but you're still at this point hiking a long ways just to get a minimum of 4 points a day. So that's another issue that we really kind of had to address. And so then we went to a phase three, Phase 3, we still utilize Geomore Funds and CLHS, but this time we confined our sampling to 19 groups. So basically we went in and identified 19 areas where we could get on a trail, hike 10 miles or less, and capture as many points within that boundary as we could. And we still utilize that off 30. So we would get on a trail, hike 10 miles or less, and still be only 30 minutes or less to a point. So that was that narrowed focus. And we, again, identified 19 groups where we could do that. And we had good success with that, but we just, at this point, didn't have enough knowledge of the DSM process. So I was really lucky that Tom DeVello came to me and to some other folks and said, hey, we're interested, the DSM Focus team is interested in doing a DSM Field Week. You know, do you have a project that would fit the needs of the DSM Focus team? And that's, you know, luckily, we were very lucky that we got chosen for the first Field Week. So we switched to Phase 4. All right, so this is the sampling same area for Phase 3 where, as I said, you know, off 30, 10.5 miles or less, and the points are a lot closer together in smaller groups. So it feels more like a transect when you're out there as opposed to just getting, you know, a point and then another 2 miles grabbing another point. So again, the DSM Focus team sort of was Phase 4 of the project. The idea of the Focus Team Field Week was to develop a nationwide network of soil scientists informed by DSM techniques. And more importantly for us was to cross-train local soil scientists and DSM experts while helping deliver a soil survey product. We wanted to develop the knowledge and expertise of us, and also because it was our first DSM effort, it was also the first DSM effort for our region. So we were kind of the guinea pig for what quality assurance looks like, how to perform a quality assurance review, how to do independent validation. We were targeting sparsely investigated project areas or having some modeling problems, and again, increase the network of point observations across the USA. And I guess the most important thing is advance the Soils 2026 effort. So that was held in September this past year, September 30th through October 5th. I'm not going to read the names. We had several people, a couple of you guys are on the call, but here's the team here. I'm sure you guys recognize some of those wonderful faces. It was a good week. I think it was definitely a week where your mind had to be open to all possibilities and realize that that your data is going to have some work. We all have legacy issues or legacy challenges. I'm not going to use the word issues. Legacy challenges with the data that we have, and so what do you do with that? And so you have to I think any DSM effort that you do, there's some need to be humble going in and realize that we all have issues. It's not just you. That was my lesson. Okay, so coming out of that, the DSM Focus team, they delivered 105 covariates that were developed. I believe Travis, Nauman, and Dave White, and I think Alex and Tom DeVello, that you guys all worked on developing the covariates for our office. Those included both terrain and spectral data. We still continue to utilize CLHS, but we based the CLHS or the condition Latin hypercube sampling on the new covariates that were developed. We implemented the group boundaries as we had done previously, but we applied new CLHS scripts that essentially used a seed that would make our data reproducible. So one of the things that we were doing early on, even every time we would run CLHS, thinking that we were getting the same points, we weren't. So the really key thing to this is to make your results reproducible for somebody else. So that was a big learning lesson for us to implement the seed. We applied the CLHS to the U.S. Forest Service portion of our project area, and then use data reduction methods to eliminate covariates that were either highly correlated. So we had used 3 of them: near zero variance, a correlation matrix, and principal component analysis. So we completed our PET-ON cleanup and field sampling May 2019, this year. We initially started out with about 359 NRCS PET-ONs. Through stringent basic PET-ON cleanup, we narrowed that down to 152 PET-ONs that we had available for use in the modeling or training development, model training and development, excuse me. So of the 152, 25 were legacy site PET-ONs. Those were PET-ONs that were already in NRCS that had distinct lat longs and didn't share, were not being shared through several counties. And of that 152, 127 were sampled through our field sampling in 2018 and 2019. We utilized random forest to develop a class map based on 4 classes, and we also did independent validation. At the end of our independent validation, we had a total of 78 validation points. So basically, we did 1 week where we had 3 teams, and during that week, we collected 60 sample points or validation points. And then we also included a separate 18 legacy PET-ON site descriptions that were not accounted for in the training of the model. So these 18 points were not in NRCS, but they had complete descriptions, and so we were able to use those in our validation. The reason why they didn't get put into the training model is, I'll talk about that later on, but they were good enough to be able to be used in the validation. So let's get into the model itself. I talked about, the classes. We had 4 classes, so I have those described at the top. Anakisa Lefty, that was class 1. Breakneck Pullback, that's class 2. Sakana Lefty, Geo Catalucci, class 3. And class 4 is the high Antuga Chiltowski. That's your colluvial soil. I'm not going to read all of the covariates, but those are the covariates that we use. Some of it should be pretty familiar to you. Slope length is one of them, the slope degree. One of the important ones for us was the terrain ruggedness index. That was a good one that helped us with our project. So we talk about out-of-bag error using your random forest model. So when we think about out-of-bag errors, after we run the random forest model, what is the confusion? What is the error in the classes? So this out-of-bag error was based on 4 classes, 17 covariates being used, and 152 observation points. So we ran random forest using 500 iterations, or trees, 500 trees, and then we are able to run a confusion matrix and look at what our out-of-bag error is. And so that gives us an out-of-bag error of 32.24%. So if your standard for accuracy is 60% and your out-of-bag error is around 32, you can make some or infer an assumption that you might be close to having a good model. I will tell you that we ran this for several days, several random forest models over and over and over again until we came up with one that we felt like worked the best. All right. So if I want to cross-check using a split method, so instead of an independent validation where we're basically going out sampling points that are completely independent from our training points, okay? The split method uses a method where we can run a script and split out 25%. You can actually set the threshold for this, but basically it's splitting out 25% of the 152 that we have available to us for testing the model or validating the model, and 75% of those points randomly selected for training the model. So if we do that, then what we get is an out-of-bag error around 34.78%. So our out-of-bag error increased a bit, although not much. And so what we're looking for here is to test the model that's developed there to see how it differs from the one that utilizes all points. And what we found was that the model utilizing all points seemed to paint a better picture of what we know is really happening on the ground. And then again, so if I run a confusion matrix based on the split method, I see that my overall accuracy is around 62%. Again, within the threshold, but it's not really where, I felt like we could be. So again, we didn't use the split method. We decided to throw all 152 into the training of the model and use independent validation to get our validation points. So based on our independent validation, again, using 78 points, 60 of which we sampled, 18 were legacy points, we got our accuracy, overall accuracy, to around 79%. So we were very pleased, and I think very shocked when we went out to the field. I think all of us, at least my field staff and I, went into it a little bit nervous, wondering if we could trust the machine since this is the first time that we'd ever done it, wondering what we would get, a little nervous about what people would find, and then also a little nervous about, we as soil scientists have our own biases of what we think what we're used to seeing when we're in the field. And I think we ended the week pleasantly surprised that everyone was able to take away their own bias and come and actually sample and find exactly what we were hoping they would find and verify that what our model had done had at 79% accuracy was pretty daggone awesome. And so here is the example of the model itself. So there are the class predictions that we made. The blue is the colluvium. And then, so you've got your different classes, but I just want to notify just to show you that the blue is the actual colluvial portion of our classes. And then if we compare that to the existing Circo, you can see that there's a lot more detail that is provided by the raster class map and still verified, and again, at 79% overall accuracy. So let's get into the lessons learned and knowledge gained. The first thing is your project boundary. What we learned was extend the boundary for the covariate development, but pull it back for model development. That's what we learned. Now that might not work for everyone's situation, but going into DSM Field Week with the DSM Focus team, we had a very specific boundary that was based on soil. So it wasn't based on a watershed. It was based on the soils and the existing circle that was already there. And the real issue with that is that when you're developing covariates, you want continuous data. So we were breaking watersheds based on where a soil line was dropped in half. And so we weren't going to really get a true picture of continuous modeling or continuous data. And so for us, the project boundary, again, extend the boundary for covariate development. But when we actually tried to use the purple boundary, which is what the DSM Focus team used to develop the covariate, when we try to use that, we just don't have enough points in that entire area. And we specifically didn't sample any points outside of the actual project area or project boundary that we wanted to use. So in this map here, the purple is the DSM Focus team boundary for covariate development. The red one is the original project boundary that we had established based on those Arcos or Anakeesa geology soils greater than 950 meters. We ended up having to go in and actually fine-tune that boundary down for our modeling efforts down to a project area of about 1,240 meters. So basically soils in an elevation greater than or equal to 1,240 meters. And the acres within that blue area is about 179,000 acres. So for covariate development, we started out thinking the only covariates that we were going to use were going to be Geomore Funds. It was going to be, or your landform model, slope, and maybe aspect in the end. And as I said earlier, when we got into phase 2 and 3, we were only using slope and the landform model. And so we had an opportunity to take Intro to DSM after our DSM Field Week, and we realized that you have to, if you're going to do DSM, you've got to utilize ScorePan. So you're basically still looking at the soil at a specific point in space and time, but you have quantitative function of environmental covariates. So you can quantify the function of soil, climate, organisms, relief, parent material, age, and then importantly, the spatial position of that data. It also is an estimation of error or uncertainty. So we can go to a pixel and estimate the uncertainty of that pixel for that class. In our field data collection, I think this was probably the most humbling experience. We thought, okay, we can go to these points, we can hike these miles, we're going to be good to go. What we realized was the terrain was a lot more rugged, and we really couldn't hike as many miles as we thought we could. We still did, that 10.5 miles. Towards the end of our project, we were at our 12-mile range. But accessibility is always going to be a challenge, so we were constantly having to go back to the drawing board, or at least it felt like going back to the drawing board, to figure out how we can sample as many quality points that we could sample and not kill ourselves. And so just for instance, from right to left, you're talking about at least a 14-mile round trip that we would have to do in a day. And physically it's not. It just wasn't possible. Our maximum amount of points that we could sample in a day really was 4 points and do about 10.5 miles to up to 12 miles round trip. We also learned that less is not more. So when we started our field sampling, we had developed a PET-on description form that pretty much threw a bunch of stuff out. We said, okay, we're just going to grab color, texture, maybe fragments, and we're going to move on. And what we realized is that we really had to rethink what we were getting when we were in the field. When you get out there, just because you want to make more efficient use of your time, you can't forget to be a soil scientist and not get a complete picture of the data or the information that you're getting from each of those sampling points. And that means looking below the ground, above the ground, and nodal points around the point that you're at. You want to be precise, right? So your model depends on your precision. So if you're guessing or you're cheating, your model will tell you that you cheated and you guessed. One of the things that happens often with some of the legacy data is that we ran transects and we put the locations on a map and we drew a line, but we weren't necessarily accurate with where we drew the line. And so what happens with that information is that when you try to use it, you're basically telling, when you're training the model, you're basically saying at this point, the stack of all these environmental factors equals this class at this point. And so if you've guessed and you were wrong, you basically are training a model based on an error, based on a guess. So you can imagine that your accuracy is not going to be very good. It also confuses the model. So you're going to get models that look a little bit wonky. And so when I talked about the 18 legacy points that we used in the validation, the reason we were able to use those is because in theory they were correct. but when you try to apply them to training of the model, then you get some real wonky issues with your actual model that develops. It puts pixels, tiny little pixels here and there because it's confused at this point, because even though it's within the class, it basically can't figure out where on which side of the class it's going to be. Again, you want to think 3D. You want to think what is below and what is above the ground. But less is not more. Get the whole picture. Put all of the vegetation down. Take pictures. Write it all down. And again, I think we've all heard this, crap in equals crap out. So if you guess and you're not accurate and you're not precise and you can't put it on paper or take somebody else to the same spot, then you basically have put in and crap out. The project area was 178,380 acres, just to answer that question. The other thing that we did during our field investigation was to develop a decision tree, which Dr. Thompson kind of keyed us in that would be helpful to us, and he assisted us with that because he made his own during the DSM Field Week, which was very helpful. So we developed a decision tree. I say we, but actually it was one person. Developed a decision tree for us to use when we're out in the field. We knew what catino soils that we were dealing with, so that made it easy for us to identify the difference between soils based on depth, restricted layer, and whether it was fine loamy or loamy skeletal. So as far as the PET-ONs and the site data, it is 100% absolutely necessary for you to spend quality time on every single description, site, and PET-ON. Go back to the files. Go back to the filing cabinets. Go back to the original descriptions. Verify the lat longs. Verify what they were finding. Are there any other notes that would assist you in inferring what they were trying to classify it as? Because some of the descriptions that you might have may have been taken early on in the soil survey when all of the series hadn't been established. So go back to the original data if you have it. Verify those lat longs, because as I said, if you're not precise about your lat longs, you're really basically developing a poor model. You're developing a model that is a guess. Are there duplicates or overlapping PET-ONs? So, going to the MLRA theory, we had some PET-ONs that were shared across several counties, and so the issue with that is that doesn't, even though they appear to be 4 separate sites or 4 separate PET-ONs, they really aren't. They're just one. So we actually ended up with a lot of duplicates, and going back to the notes, they still were duplicates in the notes as well. And again, crap in, crap out. So for the covariate selection, this was a lot of fun. We have 2 kind of schools of thought. So you start with the score pan. I mean, that's in all A's. You start with score pan. We didn't know about score pan necessarily when we first started our project, but we did learn later to use it. So there are two schools of thought. There's one school of thought that says throw all the covariates in and allow the machine to decide which ones you need to use and which ones you don't. And there's another that says use your tacit knowledge to select the important covariates that are going to actually drive your model. And so you have to decide which one of these you are, or maybe you're both. And so we decided that we're both. So ultimately, the thing that we have to ask ourselves, and the thing we had to continue to ask ourselves was, can we explain what we did and why we chose those covariates? And so initially I started out using all 105 covariates. And I was using all these really great tools like recursive feature analysis to eliminate covariates. But I couldn't tell you why it was picking them or why they were getting eliminated. And Suzanne really helped me think about what was going on there. and how important it was to use my own tacit knowledge and keep it simple. So that's what we did. We went back to the drawing board. We sat down with the list of covariates that we had and just went through them to figure out which ones we were going to use. We ran iteration after iteration after iteration, model after model after model, using different covariates, trying to figure out which one was giving us the best accuracy, but also painting the best picture that we knew existed in the field. And we did some elimination of our own based on continuing to run random forest models and seeing that every time we run it, it's telling us that this is not an important covariate. It's not really telling us anything. So you have to give it some time, and you have to go through your covariates and really utilize FloorPan to give you the covariates that are going to tell you the best story. All right, so Geomore Funds. We absolutely love Geomore Funds. I was like, Geomore Funds is the greatest thing that ever happened to our office, but it isn't the greatest thing that ever happened to random forest models. So I'm going to show you why. I'll start with, as I was talking about running all these high-tech scripts or codes to develop a model or select a covariate. And Dave White, I love him, and he is great at what he does, and I am not on his level and not afraid to admit that. So he wrote this script, and it was excellent, but I couldn't explain to you what it was doing and how it was doing it. And that's when Suzanne said, look, you just have to keep it simple and go back to the basics. So we did. So this was actually the covariate reduction based on high correlation. We went through the covariates used. And so, I'll stop here. So again, not to get too far off task, we basically went through, like I said, all the covariates. We went back to the drawing board, used a more simplified random forest model, and those are the covariates that we came up with that we were going to use. This is the random forest model right here. Basically, it's just very simple, using 500 trees, as I showed you before. Here's the estimated out-of-bag error. And I know there's some question. If you actually look at our covariates, we have this NDVI off, NDVI on, and then NDVI_C, which is the combination of the off and on. And I remember Suzanne asking me why we use them. It seems like that's kind of redundancy to use the combined when you have the off and the on. And we tried taking the combined out, but what we found is that every time we would run the random forest model, it always wanted those three together and always gave us the best product. So that's why we kept it. So I talked about Geomore Funds. This is the example of Geomore Funds broken down into 3 classes. So Geomore Funds gives you 10 classes. I've broken it down to 3 classes. And the reason I'm showing you this is that it is an unsigned integer. So even if you make it a factor in your random forest model before you actually do the modeling, what happens is it has no idea what to do with those integers. It just doesn't understand what to do with them. So the result is what you see right here, a big box. That's what Geomore Funds kept giving us. So unfortunately, we had to remove Geomore Funds. But I do think that Geomore Funds is a reliable and consistent layer to do analysis. And maybe in a more rule-based approach, that would be a good layer to use in your rule-based approach. So in your model training and development, I can't emphasize this enough, is to have faith in yourself and the machine. So as I said, in your covariate selection, the 2 schools of thought, right? Let the machine decide or you decide. And I think you have to have some faith in both yourself and the machine. What we learned from validation was we should have had faith in the machine and not worried so much about it being correct, that we were on the money more than we thought. Ultimately, again, can you explain what you did and why you did it? The other part of this is correlation, correlation, correlation. I think that's one thing that we forget to include. So this should be an iterative process, meaning you shouldn't do it at the end. It needs to be something that you do from the start and at the beginning, the beginning and the end. Correlation decisions and quantitative results. That means that I'm going to make a correlation decision, for instance, in our project, Anakisa Lefty, that's our correlation decision. And we can quantify that. We can quantify that with our model. We know that based on the confusion matrix and our out-of-bag error, we know how accurate we are in that correlation decision. We tried modeling all of the classes independently, and what we found was we just don't have enough information to know where those separations exist because they can exist in the same environment. And again, crap in equals crap out. So this is the random forest model that we were talking about, a little bit a more complex model. Again, we couldn't explain what we were doing, why we were doing it. And this is our more, I guess, simplified random forest model that we use. And then we have the validation of the model. So are you going to do data splitting? We talked about that earlier. Are you going to do data splitting, or are you going to do independent validation? Or are you going to maybe do both? And again, correlation, 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 because your correlation decisions will drive the training of the model. It will drive the output of the model. It will drive the validation of the model. So you can't do any validation if you don't have a correlation decision made. So don't wait till the end. Make these decisions, and they're not decisions that that are set in stone. So you have to make the decisions, run the model different ways, and see what you get. You know, one size does not fit all. And again, what is the model telling you? Crap in, crap out. You see that as a theme the entire time. So I talked about what the model is telling us. So here's a lesson that we learned from our validation of the model. Our Anakisa Lefty soils, they're basically loamy skeletal, deep to moderately deep soils. They're the only loamy skeletal soils that we have. And they happen to occur on pretty rugged terrain, steep slopes. So that's where we're finding it mostly, okay? So our validation point, so I have this one point highlighted. If I zoom into it, this validation point, the model actually pulled out an Anakisa Lefty way down, near the colluvium, but it was able to pull that out in the model itself. And that was pretty impressive. And so when we went out to sample it, it actually did sample out as Anakisa Lefty. So what it's telling us is basically based on a ruggedness terrain ruggedness and slope in degrees. So if I put these two, the purple is showing us the slope. So the darker, the lower the slope, and the lighter, the higher the slope. So if I overlay the two, I'm able to see that there are areas of these really bright areas that occur that might be that Anakisa Lefty. Okay, so it's kind of indicating an area that those might occur. And so when we look at the model, these yellow areas that you see delineated, that's the model actually was able to pull those out as Anakisa Lefty. Now, are they really Anakisa Lefty, or are they just rugged areas of rock outcrops or and real hummocky, complex slopes? So when we compare that to what the terrain ruggedness index tells us, we can see exactly why it pulled it out, because it's a very rugged area and a steep slope. So our model is telling us something. So last, I will end with this. you have the DSM Focusing, I assume, Suzanne, this is all in your training of the Intro to DSM training, but your digital soil mapping, there is a stages and processes form or PDF that you can look at to help you sort of guide you through the processes and what you should do, when you should do it. All of that information is available to you. We did use this. There are some projects that I know are out there that the PEDONs already exist or the field data already exists. So you have to kind of figure out where you're going to start in this process, but I think this is a useful tool in your project planning. And that's all I have.
All right, thanks, Tiffany. And I'll remind people, if you got a question you'd like to ask, go ahead and put that in the Q&A, and we'll take those questions. So, Tiffany, there is one question in the Q&A already, and I think you covered it, but if you could just go over it one more time. How many acres was your project area?
178,386 acres.
Matt, you mentioned 19 groups of sampling sites. How were those sites grouped?
So they weren't grouped in any real order. Basically, we went through all of the trails and that existed within our project boundary. And we calculated the distance of the trails on a round trip, okay, from a trailhead. So basically what we did is we calculated every trail starting at the trailhead that we could get on that was 10.5 miles or less. So they necessarily weren't grouped in any real grouping other than it was just a polygon drawn around an area of a trail that was 10.5 miles or less that we could get on.
All right, there's another question from Anthony. What do you feel was the most limiting data layer that you used, and how did this affect the results?
Well, none of the covariates that we actually used in the end were limiting, but I think the one that we were surprised that didn't really help us as much, and every single time we used it, our random forest model said get rid of it, was rock on, which basically should identify all the rock outcrop areas. I think what happened in that one was that it was picking up on, it basically picked up on the main highway, so it was picking up on asphalt. And so it was putting rock outcrops or the Anakisa lefty stuff that I talked about being on rugged terrain. It was putting Anakisa lefty on a bunch of stuff that we knew for sure wasn't Anakisa lefty because it was picking up on asphalt.
And I'll just add a comment to that, especially because we had some thoughts in the chat about covariate selection. But, you know, the idea with employing, whether it's some of the machine-driven covariate selection methods in conjunction with your pedological knowledge, is that, you know, you're able to kind of whittle down that list of covariates of data that you're feeding into the model. So the idea is that you're not including things that will be limiting for your final results. You certainly will learn things about your data through that process, and like Tiffany said, things that covariates that often you think are going to be important and then they don't end up being important, and you know, like she did a little investigation and found out why that layer that she thought would be useful was ending up not useful. So that's why using, you know, taking the time to explore your data and understand your data and use, you know, your knowledge of soil landscape relationships in conjunction with some of these more automated approaches to looking at correlation and things like that within your data. It's a really important step of the digital soil mapping process.
All right, Tiffany, there's some more questions that have come in. And so Gary asks, what was the average slope of the project area?
The average slope of the project area based on where we were was around 65, I would say 65% slope, somewhere in between that 60 to 65% slope. There were some flatter areas that we saw, but not that many.
And the Oxnard Soil Survey Area Office says, is the covariate reduction code Dave put together on the GitHub site?
I believe it is. It's also on the DSM, Suzanne, I think, I don't know if I'm saying it right, but I believe that it is on the DSM Focusing site.
I can't remember if it's in our GitHub repository or just Dave's, but it's also linked on the job aids webpage, the NRCS Soils job aids. Under GIS and digital soil mapping, we have a link to some of Dave's scripts there.
Okay.
And Kim asks, what's the next step? Do you have to continue doing more areas to complete the entire project? In other words, elevations less than a certain level?
That particular area, that in that 178,000 acres, that one's done. The next step for that particular area is for us to get all of the NRCS, well, it's to complete the NRCS work and then get the raster published and then the SERGO published. As far as, so there is a U.S. Forest Service area that is in Anakeesa as well in that same geology. It's also in, I don't know why I didn't say this, but that entire project was in the frigid temperature regime. So there is another Anakeesa geology in the frigid temperature regime. We'll need on the U.S. Forest Service. Our permit ended on that, and they hadn't gotten us a new one. So what we did, because we didn't have enough data to really model that area since it's not attached, we'll go back and complete that one as well. And then from that, well, there are a few projects that will come out of this, and experience one being that we possibly have a high mountain hydric soil, or because the Park Service has identified some areas that there are high mountain wetlands, so maybe establishing a high mountain hydric soil. And then there are two other soils that occur in this area that are basically organic matter over bedrock. We don't have enough points to utilize to actually put that into our model, so we'll need to do some investigation on that. But that's the whole point, right? So you're getting some future field projects out of this one project that at the end of the day are going to give the Park Service a really good picture of what they have out there.
All right, just want to bring people's attention to the chat where Dave has put in the URL for the GitHub site. So if you want to copy that and paste that into your browser for later, please do that. Another question has come up from Greg. What elevations are frigid soils in your area?
Greater than 1,240 meters. So that's essentially where they occur.
All right, well, that's exhausted our questions. Tiffany, Suzanne, do you want to have any closing remarks?
Well, I'd like to say, Tiffany, great job. Very well done presentation. And then I guess I would just like to encourage other soil survey offices, if you're interested in participating in a field week project with the DSM Focus team, you can find the application on our Focus team website. And we'd love to get out and help more folks and learn more things together. And so just encourage some more participation.
And yes, it was a very good presentation, Tiffany. So thank you, Tiffany. Thank you, Suzanne, for your time and effort to make this presentation. And thanks to all the participants for joining in. We hope you found this information beneficial. We had more than 120 people join today's webinar. And as I mentioned earlier, a recording of this webinar will be available on our National Soil Survey Center YouTube channel within a couple of business days. So feel free to let your colleagues know about this training opportunity. And this concludes our webinar presentation.